Hello, welcome back to Statics Engineering 211, and I wanted to pick up where we left off last time. We'd finished up talking about trusses, and we were going to move on, continue on in the same chapter, but start talking about what we call frames and machines. And the names frames and machines, excuse me, really only are different to the people that are talking about them. A civil engineer, structural engineer is probably going to talk about frames. Mechanical engineers, maybe more so machines. And the motivation for this might be something like this. Let's say that we build a building here, and we could build it very much like a truss. So it has a couple floors in it, and then maybe some columns. A lot of buildings look like this. And what we might end up doing is we're a little bit concerned. We've got some gravity loads here from the roof. Those loads would be applied at each one from the floors and whatnot. Got a person down here to give it some scale. And you could, of course, have lateral loads from earthquake or wind or whatever that might be. And if these are pin joints, like this, excuse me again, each one of these are a pin joint, you can imagine that this could rack over. So what we might want to do is we might want to brace it. So maybe we'd put some cross bracing on it here, maybe some cross bracing here where we just take cables. This is very common. Maybe have some cross bracing here and some cross bracing there. But then we run into the problem that we can't fill these spaces. So we put these rods in here, and we've talked a little bit about how to analyze that. If that's a rod or a cable, only one or the other is going to be loaded because a rod or cable won't take tension. This is a very efficient way to do this until you think that the building may want a window here or a door there, although a door on the second floor would be kind of odd. But if you wanted a window there, that brace wouldn't work very well. It always amazed me, if you go to the library here on campus, there's actually a brace running through the middle of the library. I thought that was a pretty slick way that the architect sold that to the customer. But anyway, usually the customer doesn't want braces like this. They want to be able to put their doors and windows in where they want to. So what they might think about doing is putting some gussets here and starting to brace these joints, and you turn it into a moment frame. So let me do this on a little smaller scale. Maybe you have something like this, and you build a frame like this. This piece is a frame, and then you could still have a two-force member there. And then as you put loads on this, this is resistant to bending. This is not a pinned connection there, and it will support those loads. So that's probably more from a structural vantage point, a civil engineering vantage point. Of course, when we think about machines, that goes back to some of the equilibrium problems that we have dealt with. Maybe if you think about how a truck scale works. So we've got a deck, and I'll be very simplistic in this, but might have some arm here with a tremendous leverage. So we'd have a pivot point here, and we could then apply weights to this and figure out how much this truck weighed. Now, there's different ways that you can actually do it even electronically now. So, gotta have a smokestack. All of them need a smokestack. So if we were to analyze this arm, that gives us the tremendous advantage here in terms of leverage. So we could put a small weight on it here and balance this. Anyone that's ever used a balance understands how this works. This would definitely be a machine. So really we're going to analyze these very similarly, and it really just depends on where we're using them and what our background and our discipline is. Well, in analyzing these frames or machines, we want to ask the question, are they rigid or are they not rigid? So if we move to this page, so page number 2 here, we ask the question, is it rigid or not rigid? Okay, is it rigid or not? So if I look at something like this, it's a kind of an A-frame here, and well, maybe I'd better back up. I jumped to this a little bit early. The other thing, whether we're calling it, sorry about this, but the other thing, whether we're calling it a frame or a machine, is it has to have at least one non-two-force member. Because if it's all just two-force members, it's probably going to be a truss. But with this, I mean, if we were to look at the free body diagram of that arm that's in the scale, we have a fulcrum point, a pivot point there, probably going to have a couple of forces. We have a force like this, and then we have probably a tremendous force like that. So definitely not a two-force member. If we look at this member here that looks something like this, definitely not a two-force member. Okay, and of course, if we were to analyze, if you put these large gussets in here and stiffen this, made this what we call a moment resisting frame, it would again look a lot like that. So if it has one or more non-two-force members, it certainly is not a truss. We'd call it a frame or machine, and then we've got to analyze it differently. So how we analyze it is we ask the question, is it rigid or not? And what that means is if I take away the supports, so we take something like this nice little A-frame here, and we notice that there are several non-two-force members. I mean, this member here, right here, this member right there is loaded right here, right there, and right there, so it's not a two-force member. This horizontal member is loaded like, is supported here and there and loaded there. It's certainly not a two-force member. I mean, if we were just to draw a free body diagram of that piece, we would have a couple of forces there and a couple of forces there, and then that, definitely not a two-force member. So it's not a truss. Now we need to ask the question, is it rigid or not? Well, if I remove the support reactions here, we ask the question, is it rigid? And in fact, it is rigid. Okay, it retains its shape. You could imagine if you were to take these off, it would, I guess, fall down, and you ask the question, when it finally falls and hits somewhere and you pick it up, is it going to be in the same shape? This one would be in the same shape. It'll maintain that shape. If you were trying to make a folding chair for someone to sit on, this would not be a good design. Probably be a good design for a chair, but not a folding chair. It wouldn't fold up. It's rigid. And the way we do rigid frames or machines is we usually find the support reactions. Okay, we usually find the support reactions first, and then we start to work on individual members. Well, let's look at this other example here. Let's try something like this. Is it a truss? Well, I have a two-force member here, don't I? And I have a two-force member there, but this member being loaded in the middle is not two-force member. Certainly this member being loaded here and there by those two-force members is not a two-force member. So I've got two two-force members and two non-two-force members. So by definition, I have a frame or a machine. And I need to then ask the question, is it rigid? So if I remove its connection with its support here and its connection with its support there, is it going to retain its shape? No, you can imagine this flopping around. It'd fold up like a fat man in a lawn chair. So this is not rigid. It's not rigid. And what we're going to do is we're going to have to look at the individual members first. And one of the reasons for that is oftentimes a non-rigid one has a statically indeterminate set of support reactions. For instance, if I were to go back and look at this rigid one, I've got a pin connection, so I'll probably have a couple of forces here, and then I have a roller. So I have 1, 2, 3 unknown reactions, statically determinate. But over here I have a pin connection, so a couple of forces, and I have a pin connection, so a couple of forces. I have 1, 2, 3, 4. I have a set of statically indeterminate reactions, so I'm going to be forced to go and look at the individual members. And usually we can still solve the problem and actually then eventually get to these, but we'll have to start at the members and not at the reactions. So that's how we tackle this. The other thing that we have to be very mindful of is Newton's third law. So when I look at two pieces that are together, let's say what's going on maybe right here, or what might be going on here, or maybe what's going on right here or right here, it might look something like this. And if I take that and I look at this member on top, and we look at the pin here, if I apply a load here and say that this is AX and maybe this is AY, and I could just arbitrarily place this in, and we'll let the math take care of the negative signs, figuring out whether I've done it in the right direction or not. If I look at this other piece, this piece underneath here, and I were to go on and try and solve it, which way would those forces be? Well, I'd have to say that AY would be here and that AX would be here. Because Newton's third law says that the force of action and reaction between two bodies, this body and this body, is equal, is opposite, and is collinear. So that when I put these together, this has to cancel that, and this has to cancel that. So really remember your third law. Okay? Then what happens if one of these becomes negative? Then you could, if you wanted to, turn this around so you get a positive. We'll probably have some examples of that and learn to deal with that. But as long as all things being equal, we want to show these being opposite. If this is going to the right, this has got to go to the left. If this is going up, this has got to be going down. Well, I guess the last thing we might do is talk about how we're going to go through a problem. So if we were to build a very crude flow chart here, we might ask first, is it all two force members? Okay, if the answer is yes, we do, it's a truss, and we could do a couple different ways. We've got method of joints, and we have method of sections. Okay, and if it is fails the test here, so if it is no, that means it's got one or more non-two force members. Then we ask the question, is it rigid or non-rigid? And if it is rigid, what do we do if it is rigid? We find the support reactions. Find reactions and continue working from there. Whereas if it is non-rigid, so non-rigid, if it's non-rigid, what do? I go directly to individual members. And to some extent, we've maybe made this too complicated, too much to think about and whatnot. We're going to do some examples that will take us through this. We've already gone down this path with our trusses. We're going to do some examples, and we'll get to try both of these before we're done. And but once you get used to this, I don't know that you'll cognitively go through this, but this is the process that you'll follow. So let's try a problem like this. Got a calculator out here. So we're given this. We've got three members. We've got the member A and B and C and D. So the way that's loaded, that's definitely not a two-force member. The way this member, this horizontal member B, E, and F is loaded, that's certainly not a two-force member. In fact, the only two-force member in here is this brace, CE, and I guess this cable that comes over that pulley. So certainly not a truss. It's a frame or a machine. So if we ask the question, is it rigid or non-rigid? So if I remove the reaction here and I remove the reactions there, and you can imagine this thing falling down to the floor, the main structure here, the cable might get tangled up, but this main structure would retain its shape. So we're going to say that it's rigid. Okay? So it's rigid, so we're going to then find the reactions. Okay, we're going to find the reactions first. The other thing we have to be careful of is when we draw a free body diagram, the free body diagram is always a free body diagram of masses. No, I'm sorry, not masses, but rather forces. So I don't want this mass here. I'm going to have to take 4,000 kilogram, multiply by 9.81 meters per second squared, and I'm going to come up with, what, 39,240 newtons. You might say 39 or 40 kilonewtons, but I'll just work with that number. I think that's what it comes out to be. Yeah. So I've got too many significant figures, but so that you can follow along, I'll just go ahead and leave that, and we'll tidy up our final answers. Okay, so free body diagram is a diagram of forces, not masses. So I want to convert this mass to a force. Well, let me do a free body diagram for the entire thing. So that's going to look something like this. And here at A we have a pin, so I think I'm going to say that I have AX and AY. And then over here at D we have a roller, so I'm just going to call that D. And then out here, if this is this mass is pulling down on this force here would be, that's our 39,240. Okay, and we can get our dimensions from here. I won't clutter up this picture with them. So if I sum the moments about A, setting that equal to 0, I should have what? 5.5 times, isn't that the distance here? I'm going to have 2 or 3. And 2 gets me to 5, and then I have the radius of this pulley here, so 5.5 times 39,240. That's going clockwise, and then I would have to subtract off D times the distance that acts through, which is what? 1.5 and 1.5 is 3, another 1.5 is 4.5, and 1/2 is 5. So I could then solve for D because I don't have anything else. These two forces intersect the point where I'm summing the moment about A. So I could say that D is equal to what, 43,160 newtons. Let me double check that. Yeah, 43,164. I can just leave it at that. We have too many significant figures already there. So we've got D. If I sum the forces in the vertical direction, setting that equal to 0, I have AY minus 39,240. So AY Turns out to be 39,240 newtons. Those aren't final answers, but I want to be able to find those. And if I sum the forces in the horizontal direction, setting those equal to 0, let's go ahead and take positive to the right. I'm going to have D minus AX. Anything else here? Nope, those are the only horizontal ones. So I could say then that AX is equal to D, so that's equal to 43,160 newtons. Okay. Good. So that was all really just equilibrium. We could have done that a couple weeks ago, in fact. Nothing structural here yet, but now what I want to do is I want to take these reactions and start to apply it to the individual members. So let's see if we can do that. So let me keep this picture on hand here. We could maybe argue that, well, we should do a free body diagram for A, B, C, D, or maybe someone else would argue that we should do a free body diagram for B, E, and F. It really just takes experience to figure out which one that you want to do. I think probably before we're done, we may have a free body diagram for both of those and more. But let's start out with this vertical piece here. So I'm going to start out with a free body diagram of that vertical piece. And we've got these two forces here, like this. And then at D, I had a force like this. Let me put those in. What were those? 43,160 newtons. 43,160 newtons. And this AY 39,240 newtons. Okay, so those are the reactions that we found. That's nice that we know those. Those are not then unknowns. What else is going on? Over here at this point here, I'm going to have a force that's equal to the tension in that cable. I will say something like that. And that actually, maybe we should look a little bit at that. If I were to do the free body diagram of this pulley, what's that going to look like? Well, I have this, that's 39,240, and I have this, and then I have a pin. I've got a pin right there, so I would say that I have this force, and I have that force. I could say that this is F sub y, and this is F sub x. If I were to sum the moments about this point there, and I have a constant radius, and maybe I'll just do this once here, sum of the moments about the center line of that pulley is equal to 0. We know that that's going to be 39,240 times whatever radius we have on that, minus this tension here, times whatever radius. Hopefully this is round, and the radius from there to there is the same as the radius from there to there. So we could say, of course, that T would be equal to that 39,240 newtons. Most people recognize that just by inspection, but that's how you would prove it. If you wanted to sum the forces in the vertical direction, setting those equal to 0, you would conclude that Fy, weird looking F there, that Fy is equal to what? 39,240, and that Fx, once we recognize T is equal to that, sum of the forces in the horizontal direction is equal to 0, so Fx is going to be equal to whatever T is, 39,240 newtons. And I guess those are final answers. If we're looking for the force at the pins, those are the forces at pin F. So with that, I can come back over here and talk about this T, 39,240. And what else do I have? I have at B, I have a pin, don't I, at B? So I could say that I have BX here. And then maybe I'm going to need a sharper pen for this. I would have BY. Okay, so I got BY going up, I got BX going to the right. I'm not sure which way those go. I just put those in, let the negative signs fall where they may. And then the last thing is, we mentioned this was a two-force member, right? A two-force member. So I could come down here to C, and I could talk about C having a CX and a CY, but then I introduce two more unknowns. Whereas if I can deal with C a little differently, I'll only have one more unknown and three total. So let's use C as that two-force member. So I'm going to say that this is C. That's acting along this axis here. And we'll talk about this angle theta. Okay, talk about that angle theta. So I think I can get theta. We could maybe I'll borrow a little spot here on the original picture, and theta would be that angle, which is the same as that angle there. So theta is going to be equal to the arctangent of what? The opposite side, which would be 1.5, over the adjacent side, which is 3, right? Which gives me 26.6 degrees. Let me double check that. Yeah, 26.565. We'll just call it 26.6. So we've got theta, 26.6 degrees. So I've taken care of D, I've taken care of what's going on at C, I've taken care of the pin at B, and I've taken care of the tension, the cable there, and A. Okay. Well, let's see. As far as finding the force in all the pins, I know what A is. I've got those answers, don't I? That's AX, which I guess is a final answer, and AY, which is a final answer. That tells us those forces. So we've got this done. We already done F. That was over here. We will hopefully get B. If I get BX and BY, we'll have B done. Let's be optimistic and say we get that. We get C. Once we get this, we could resolve it into an X and Y if we wanted to, or we'll just leave it like that. So we have C, and we have D. That's right here, don't we? So that's a final answer too. So we're coming along nicely on this. The only thing that we're not going to know is we're not going to know E, but I think we can get E without doing a free body diagram of this entire piece here. So let's carry on then. What should we do with this? What's a good way for us to proceed? What if I sum the moment about B? Setting that equal to 0. I picked that point because I don't know BX and BY, and if I get C, then I could really just sum forces in the vertical and the horizontal to get that, right? Lots of different ways to do these. I mean, we could sum the moments about this point and come up with one equation with a couple unknowns, and then sum the moments out about another point and solve them simultaneously. But I think I'll sum the moments about B, and that will allow me to get an equation with just C in it. So what's that going to look like? I'll go ahead and take clockwise as positive, and I will have let's see, 39,240 times what, 0.5? That distance there, yeah, 0.5. So that takes care of that one. Then I'm going to have minus 43,160 times a distance of what, 2, a half and 1 1/2. So I've taken care of that one, I've taken care of that one. This one intersects it, BX, BY intersects it. This has to be accounted for. That's going to be a minus 43,160 times the distance from there up to B, which is from there to there is 3. And then I have plus C times the cosine of 26.6. Let's put that in parentheses so I don't lose that C. So C times the cosine of 26.6 is the horizontal piece of that, and that's going to be acting through 1.5. All right. What about the vertical piece, C times the sine of 26.6? That would be acting along there, right? That would intersect B. So I can say then, I should be able to solve C and say that C is equal to 43,160. When this moves to the other side, it becomes positive. When that moves to the other side, it becomes positive. So I have 2 plus 3. And then I have to subtract off 39,240 times 0.5. And I better divide this whole thing by 1.5 times the cosine. 1.5 times the cosine of 26.6. So let's see what that turns out to be. So I got C as 146,238. Is that what I got in my notes? Yeah, I think so. Let me double check this here. So 43, double check the work. Yeah, I think we're good. About 146,000 newtons. We'll get back to a reasonable number of significant figures and say that C is equal to 146,000. We should probably say 146 kilonewtons, but I'll just say 1,000 newtons. Okay, so that's what we have going on at C. And interestingly enough, that would be what we would have going on at E. So maybe I will just write this as also E. Okay. Well, let me finish up this then and deal with Bx and By. So what are we going to get with Bx and By? Okay, set this aside. If I sum the forces in the vertical direction, setting that equal to 0, what do I have? I'll take positive up. I have then 39,240. That's going up, plus By minus C times the what, sine of 26.6. So I can plug in, and it's up to you whether you plug in this number. I'd probably put that one in so we don't have quite as much round off. 146,238. And when we do that, By turns out to be equal to let's see, 26,239. And again, let's get a reasonable number of significant figures here. We could say 26.2. It's 26,200 newtons. Okay, 26,200 newtons. Good. And lastly, I think I have room to just slip this in here. What if I were to sum the forces in the horizontal direction, setting that equal to 0? What do I have? I have 43,160, taking positive to the right. Then I'm going to have to subtract off 43,160. So I've taken care of that one. I've taken care of that one. I'm going to have to add to that 39,240. So I've got that. That's vertical. BY is vertical. I'd better add BX and then subtract off C times the cosine of 26.6, right? So I have an equation there. Let's see, I'm adding this and I'm subtracting that, so I get to drop those out. And I could say then that C is equal to, move that to the other side so it gets rid of the negative. No, I'm not looking for C, am I? I'm messing this up. Okay, so BX. What's BX? Is equal to C times the cosine of 26.6. That goes to the other side, and then I have to subtract 39,240. So we've got, then we'll make a substitution for that. What was C? I'll go to this number again, 146238. If you wanted to substitute this in, you could. And let's see what we get for a final answer here. So BX turns out to be equal to 91,519. So we could call that 91.5 kilonewtons, or 91500 newtons is BX. Let me double check those last couple answers. BX, yeah, and then BY, yeah, good. So we've got the values for B. I guess I guessed right here. I didn't have any negative values. Had we got a negative value, we would just know that it's actually in the opposite direction. But we were able to find those forces. Now, what can you do with BX and BY? Well, you could resolve those. I mean, we have a BX going like this, and you have, that's not BX, there's BY. So you've got BY going like this, and you have BX going like that. So you could resolve it, come up with that force, and that would be what you would need to design the pin for so it didn't shear through. And we'll talk about that kind of thing in spring term when we get to strengths and materials. But being able to do this analysis to come up with these values, what each pin is, becomes very important if we start to think about designing the bearings, maybe down here at this roller, or designing these pins. So a good problem. An example of a problem that was rigid, and we started with the reactions, and we've got a couple more problems to do in the future, and that's where we will go next time before we start looking at distributive loads. So take care till then, and thank you for watching.